Hello everyone and welcome back to part 4 of chapter 28. In this video we want to take the idea of a force acting on a current carrying wire. So just to review from the previous video, we took our expression that showed the force on an individual charge that moves through a magnetic field with velocity v, and we updated this to consider a current that travels through a displacement of L, and this displacement would be the length of the wire, but that length does have to be in the direction of the current. And then if this wire is placed into an external magnetic field, so we'll go ahead and put in some magnetic fields here. These pictures can get a little crowded, but each of these X's is going to be a magnetic field line. Our current is passing through, traveling upward. So that is the direction of our displacement vector L. And then we can apply our cross product method, where the first vector is the index finger, second vector is the middle finger, and thumb, all of your right hand, will indicate that this wire will have a force acting on it, which points to the left. So we want to take this idea of forces that act on current carrying wires, and we want to develop it a little bit further. And what we're going to do is we're going to make a coil of wire. And I'll have to redraw that part. So we have a coil of wire which is currently flat, and we're going to connect some pivot rods to this coil of wire. And although I say coil, we have a tendency to think of coils as being like solenoids. Really, all we need for this discussion is some kind of a closed loop for our current to travel around. And we're going to designate dimensions of each side of the loop. So the sides where the pivot rods are connected, I'll call these dimensions A. And then on the sides left and right, we'll call those dimensions B. I just want to be able to differentiate between the two different side legs. They could just as easily be the same dimensions, but again, we want to differentiate between the two sides. And then these pivot rods that we have connected to either end of the coil will allow the coil to rotate in one direction or another. That direction has not been specified yet, but we're going to allow this coil of wire to rotate in the presence of some external magnetic field. And to accomplish that, we're going to set up two very large magnets on either side. And the magnet that is on the left-hand side of our diagram will have its north pole sitting next to the coil, and the magnet on the far right side will have its south pole next to the coil. And this will result in magnetic field lines traveling across our coil. So all of these are going to be our magnetic field lines. Now, what's going to happen to the coil as the magnetic field operates on it? Well, if there is no current traveling through this coil, then nothing's going to happen to it. And that's because right up here, our equation says that we have to have some amount of current traveling through a length of wire, and that length of wire has to be inside of some magnetic field. Well, the magnetic field part has been established, and the length of wire has also been established, believe it or not, because we have 4 different sides of this coil. 2 of the sides are of length A, 2 of the sides are of length B. So we know what the length of each segment of wire is. We just need to introduce some current. So that's what we'll do. We'll introduce some current, and we'll say that the current is traveling in this direction as it goes around the coil. And somehow we will magically allow this current to rotate around the coil perpetually. This is not something that would actually happen in real life unless this coil was made of some kind of superconducting material. Well, now that we have current running through all 4 legs of this coil, we want to see what's happening in terms of these magnetic forces. This is the reason why I chose a rectangular shape for the coil, because I want to see how each leg of the coil is affected by this cross product method. Now I'm going to go ahead and redraw these currents. We know that it's traveling in kind of a counterclockwise direction, but I want to specifically show how the current is traveling with respect to each leg individually. And that way we can address what's going to happen to the front leg of the loop, the back leg, the right leg, and the left leg. So each of these legs. So right here we've we'll say that right here, this is the front leg, this is the back leg, this is the right leg, and this is the left leg. All right, so we want to know what magnetic force, if any, is acting on each of these legs. Because if we have forces involved, those forces could cause the loop to start rotating along its pivot. So we've got our pivot point here. We want to know if one or more of these forces is going to contribute to allowing this loop to rotate. And if that happens, then we need to have a discussion on torque. Because torque will occur if we have any kind of force applied at any kind of radial position. So we'll talk about this later. First, we want to establish what these forces are going to be. So at the front face, we need to decide on what our values are at the front face. We're going to start with our general expression for magnetic force, and then we'll update it for the values that occur at this front face here. Now the current is going to be the same for all four legs of our coil. The magnetic field is going to be pointing in the same direction, which is to the right for all four coils. We just need to figure out what is L for each of these legs. And the direction for L is always the direction of the current. For the front face, we have our current running to the right, and the length of that wire that we're running through has a value of A. So our cross product will now be updated to A cross big B. Sorry, did I say dot product or cross product? I can't remember now. Obviously, we have the cross product in front of us. And so we need the magnitude of each vector times the sine of the angle between them. Now, vector A, this is the length of the wire, and it has to point in the direction of the current. So we have a vector A that is pointing to the right. But if vector A is pointing to the right and our magnetic field is pointing to the right, then the angle relationship between them is 0, and sine of 0 is 0, which means there's no force acting on that front leg of our loop. So now we try the same thing with the back leg. Now the back leg also has length of A. The length of our displacement vector L is the length that our current has to travel through on that back leg. So we again have a displacement vector of A, and that's pointing to the left now because the current that passes through that back leg is now traveling to the left. So our cross product is going to become I magnitude of A, magnitude of B. Sine of the angle between the two. Well, now our displacement vector is pointing to the left. Our field vector is pointing to the right. That's 180 degrees difference. Sine of 180 degrees is also 0. So there's no force acting on the back leg of this coil. Where we will see some different outcomes are for the right and left leg. I want to make myself a little more room here. For the right leg, we have our current traveling back. If we wanted to, we could say into the page, but again, it's kind of tricky trying to draw 3D on a 2D surface. But we'll say that the current traveling through the right leg is traveling backwards into the page itself, and that length of the wire has a value of little b, traveling through a field of big B. This will evaluate to the magnitudes of each vector times the sine of the angle between them. So I'll use a different angle notation here. I'll call this alpha. The angle between big B and little b. Big B is pointing to the right. Little b is pointing into the page. That should be a 90-degree angle between the two. Sine of 90 is 1. And so we have I B, big B. And that is the magnitude of the magnetic force that is acting on the right hand leg of the loop. For the left hand leg, we can pretty much just duplicate everything that we're seeing here, because the left leg also has a length of little b. And even though we're on the left-hand side of the loop now, the angle relationship between little b and big B is also 90 degrees. I'm going to call that angle beta. But the left-hand leg is now pointing out of the page, which is at a 90-degree angle with respect to our field. Again, sine of 90 is 1. And we get I little b big B. And that's the magnitude of the force on the left-hand leg. So I'll put subscripts of R and L over here just to indicate the difference between the two. So what does this mean for us? Well, I'll redraw the loop here with the pivots. Now that we know that there are forces on the right and left hand legs of this loop, we now need to know what direction those forces are pointing. And we could do this pretty easily by using what we know about the evaluation of any cross product. We know that whenever we take a cross product, that the resulting vector must be perpendicular to the original two vectors that were used to produce it. Excuse me. Well, for the right-hand loop, we had our length vector pointing backwards. We had our magnetic field vector pointing to the right. And if we apply what we know that first vector in the cross product evaluation is the index finger. Second vector in the evaluation is the middle finger. Thumb will be in the direction of the resulting vector. So what we need to do is we need to point our index finger in the direction of L, rotate our hand so that we can get our middle finger pointing to the right. And then the only way that I can get my thumb to point perpendicular to those two vectors without breaking anything is to have the resulting force pointing down. So there will be a force acting on the right hand side of this coil, and it will be pulling down on the coil. If we look at what is happening to the left hand side of the loop, we have our displacement vector L coming out of the page. We have our magnetic field line that is still pointing to the right. We'll go through the same method of evaluating the cross product. We now have to have our index finger pointing out of the page, so towards you. Point to yourself, then point your middle finger so that it's pointing to the right, keeping your index finger pointing towards you. And the only way that you should be able to extend your thumb is up. And so that means that the left-hand side of our loop has a force vector acting on it, which is pointing up. Well, what happens when these two forces are applied to this loop? especially since we have the um, oops, especially since we have this rod that the loop can rotate about. Well, the force on the right is going to cause the loop to start rotating in a clockwise direction from our perspective. Likewise, the force on the left is going to cause the loop to start rotating in the same direction. So these two forces are going to combine to provide some net amount of torque that acts on the loop. So that is the next portion that we need to talk about, is how much torque are we going to see acting on this loop. All right, so we'll hold on to these values right here. As it turns out, both of these forces have the same magnitudes. They're both using the current times the length of their specific side legs. We said the left and right hand legs had length of little b, and we have the magnitude of the magnetic field itself. So there's the magnitude of the forces. Now we have to apply those forces using the torque expression. And torque is also a cross product. Torque is the cross product of the radial vector times the force vector. And this means that we can evaluate using another cross product evaluation. In this case, the angle will be the angle between the radial vector and the force vector. Well, where's the radial vector? I can see the force vectors in the diagram, but where's the radial vector? And when it comes to any problems involving torque, finding the radial vector is pretty simple. What I'm going to do here is I'm going to draw an imaginary line that goes through the two pivot points. So this is going to be the line about which our coil will rotate. So that is the pivot point of this coil. And it is from the pivot point that we have to measure out to the location where our force has been applied. And our force is going to be acting on that length of wire right there. Well, how far is that length of wire from the pivot point? And if we look back at our original diagram, we said that the front and back legs of this coil had a length of A. So from one side to the other, that's length of A, which means that we have length of 1/2 A. As this loop, or as this coil starts to rotate, that A/2 value is going to become the value of the radius of the circle that this loop passes through. So there's our radius vector. It has a magnitude of A/2, and it points in a direction radially outward from the pivot point. So that's the radius for the bottom force. What's the radial vector for the other force? Well, that other force is also being applied at a distance of A/2. It's just got a radial vector that's pointing in the other direction. But that's okay. It doesn't really matter what direction the radial vectors point. What matters is what the angle between the two vectors is. And if you look right now, those are both 90-degree angles. So we're thinking, okay, this is nice. We have RF, sine of 90 is 1, so that's the torque, right? Well, that's what it is right now. But what happens when this coil starts to rotate? What happens when this coil rotates, let's say, 90 degrees? So we're going to allow this coil to rotate 90 degrees. And when that happens, our picture is now going to look something like this. We still have the front face and the back face, but the left face has now become the top face of the coil, or I guess I should be saying legs, not faces. And the right hand leg of the coil has now become the bottom leg of the coil. So call that bottom and back. If our coil has rotated, but we still have current running through it, and these would be the respective directions of the current. So these haven't changed. You can compare these to what we had up top there. If we take our original picture and we rotate the coil, this left-hand leg is going to end up as the top leg. The right-hand leg is going to end up as the bottom leg. The front leg remains the front leg. The back leg remains the back leg. So that's what our new picture looks like after this coil has rotated 90 degrees. The magnetic field lines are still there. So what does that mean for the forces that are acting on the four legs of our coil? Well, at this point, hopefully we can kind of eyeball what should be happening for each of these legs. For the front leg, I have current traveling down. I have magnetic field pointing to the right, and so the resulting magnetic force on the front leg would actually be pointing along the pivot. And that's not going to contribute to the pivot rotating along that current direction that we have established here. We said that this pivot was rotating in a clockwise fashion, but if we start pulling along the pivot point, that's not going to contribute to any rotation. Likewise, for the back leg of the coil, we have our current traveling up. Magnetic field is to the right. There will be a force acting on the back leg, but it will be pulling in the other direction along the pivot point. So we're still not getting any contribution to rotation from the front and back legs. And if you're not quite convinced of that, try applying those forces to the torque expression. And what you'll find is that each of those forces has been applied at the pivot point, and at the pivot point, the radial vector is 0. We are 0 measure from the pivot point. That entire blue line where our pivot points are at, that's where we have to start measuring our radial vector. But we still have some forces that are going to be active at the top and bottom legs. At the top leg, we still see our current traveling out of the page towards us. Magnetic field is still to the right. We're going to see a magnetic force pointing up. At the bottom leg, we have current going into the page, magnetic field to the right. There will be a magnetic force pulling down. At this point, if we try applying the torque expression, the radial vector and the force vector for the top leg are running parallel to each other. That's an angle relationship of 0. The bottom leg has its force vector and its radius vector pointing down. They also have an angle relationship of 0. And so none of these forces acting on the coil are actually going to contribute to any further rotation. This coil has now reached a new equilibrium position. The reason I bring this to our attention is that as we rotate the coil, the angle relationship between our radial vector and our force vector is constantly changing. We started here and there was a 90-degree angle between our radial vector and our force vector. But by the time we rotated the entire coil by 90 degrees, well, now the angle relationship between our radial vector and our force vector is 0 degrees. And this means that in order to evaluate the torque on this coil, we have to leave it in that general form of sine theta. As we rotate, theta constantly changes its value, so we have to leave it as sine theta. Obviously, we start with a maximum amount of torque, which is equal to RF, but then we ended up with a minimum amount of torque that was equal to 0 because none of the forces were contributing anything anymore. Okay, so why is this important? Well, now we can describe the torque that is acting on this coil using our Physics 2 information. This was actually a Physics 1 expression. We want to update it for our Physics 2 information. We said that the radial position, when we looked at the radial position that our forces were acting on, the radial positions were A over 2. So I'm going to replace the magnitude of the radius with A over 2. I'm also going to replace the force with the magnitude that we established for force back about 20 minutes ago. We have I, little b, big B, and then we have the sine of theta. Keep in mind that this is only for one of the forces. We now have to add the contribution of both forces together. But both forces have the same magnitude, both forces are applied at the same radial distance of A over 2, and both forces will maintain the same angle relationship during rotation. If I want to get the net torque, all I have to do is take the value of one of them and double it, because they are combining to help this coil rotate in that clockwise direction. So all I have to do is drop the 2 in the denominator, and I will have the full net torque that acts on this coil. So we'll drop the 2. We have little a, I, little b, big B, sine of theta. Now comes the part where we want to clean stuff up. Right now this is only a magnitude. To clean this up, here's what we're going to do. We have the current. That part hasn't changed. We have the magnetic field that the coil is sitting in. That part hasn't changed. But if we notice, we've got the product of the dimensions of our coil. We had defined our coil as having side lengths of A and B. And that means that we have the cross-sectional area of the coil. A times B is the cross-sectional area of the coil. And I am going to write it as such. Big A is going to be the cross-sectional area of the coil. If you remember, in past chapters, we have used the cross-sectional area as a vector. If we look back at our original picture, the area of this loop, let's see if I can, I'll use pink to highlight the area of this loop. If we take the area of this loop and then ask ourselves, what direction is that cross-sectional area facing? Well, it's facing a direction that is normal to the cross-section itself. And we were able to take that idea and use that direction to define the area vector that is associated with that cross-section. As the loop rotates, the area vector will rotate with it. This is to our advantage because we can now take everything that we've put together in our equation and we can say, well, we're trying to produce a vector called torque by combining the current in the wire with one vector called the cross-sectional area vector and another vector called the magnetic field vector. And I did forget to bring the sine theta down with this. My apologies. This will help this make more sense. Because how do I take two vectors, multiply them together, and make another vector? Well, you do that by using the cross product. And the cross product utilizes sine of theta. So what we have here now in defining the torque is I times the area vector crossed with the magnetic field vector. So we can drop the absolute values now. And we're really close to having an expression similar to what we had for the electric dipole. I'm not going to review the electric dipole. You can do that on your own time. But the torque expression for an electric dipole was P cross E. And P was the electric dipole moment. P was the combination of the charge and the displacement that existed between the two charges on the dipole. And then we could evaluate this by taking the magnitude of each along with the sine of the angle between them. We could also evaluate the change in potential energy for the system using the dot product of those two vectors. And the dot product would utilize cosine of the angle between them. I'm going to use magnitude here because depending on which way you rotate, your potential energy can either increase or decrease. But over here we're dealing with magnitudes anyways. Well, is there some way that I can take what we've already learned from the electric systems of an electric dipole and treat this coil like some kind of magnetic dipole? And really the answer is kind of staring us in the face. We have electric field versus magnetic field. We have cross product and cross product. The only thing that's left is to have our electric dipole replaced with some analog for a magnetic dipole. And, well, that's what we have there. The combination of current and cross-sectional area of our coil is going to be the magnetic dipole moment of the coil. And we're going to call this mu. Back in Physics 1, we used mu to represent a friction coefficient, but now it's going to be our magnetic dipole moment, and that is equal to IA. We can then replace IA with mu. Because A is a vector, mu is a vector, and we now have a way of representing the torque by using the dipole moment, the magnetic field, and the sine of the angle between them. And then, believe it or not, all of the math that we used to define the change in potential energy for the electric dipole is going to follow suit with what we have for the magnetic dipole and the magnetic field. So we will be able to describe the change in potential energy for the system by using the dot product. And this saves us about 30 minutes or more having to go back and essentially redoing the same derivation that we did for the electric case. Now there is one final amendment that we need before we can call this good. One thing that we could potentially have with our loop or our wire, I should say. Let me zoom in on this here. I know this is getting really messy, but I only have one more thing that I have to write. We have this current that is going around the loop perpetually, but who's to say that we only have to have one loop? Why can't we have multiple loops that go around this coil? And every time we have current going around this loop, that's another combination of forces that are going to contribute to the rotation, which in turn will produce torque, which in turn will contribute to, I'm going to come all the way down here again, which will contribute to the final expression here. This is a very easy fix because what we have for our magnetic dipole right now only considers one loop. But if I included a second loop with the same dimensions, with the same current, exposed to the same exterior magnetic field, I would get the same amount of force acting on that second loop as I did the first one. And all that would happen is that we would see the torque increase by some integer value of n. And n would equal the number of loops that was present inside of our coil. And so finally, our dipole moment would need to be defined as the number of loops n times the current times the cross-sectional area. The reason that we want to write this as A is that it no longer matters that we have a rectangular loop. I could have had a square loop where all four sides were equal to A. I could have a circular loop. In that case, the cross-sectional area would be pi r squared. Well, aside from the actual dimensions of that cross-sectional area, it's still the value of the cross-sectional area that is going to contribute to all of these expressions. And this now brings us to the end of the chapter 28 material. In the next chapter, chapter 29, we're kind of going to reverse things, because in this chapter, we've been talking about how a magnetic field will affect current, and that's mainly been with our force expressions. We had QV cross B, we had IL cross B. So this was for a single charge. This was for a wire with current. So in the next chapter, we need to discuss how current can produce a magnetic field. So how will a current that is traveling through a wire produce a magnetic field? And then we're going to continue with that idea, and we're going to ask, well, how will a magnetic field produce a current? So this is going to be chapter 29. This is going to be chapter 30. But if we can produce a magnetic field by using the current in one wire, does that mean that one wire can affect another wire in the circuit? And the answer is absolutely, because we've just talked about that. The only thing that we didn't cover here was where this external magnetic field came from. We just said, you've got a magnetic field that's being produced by a couple of magnets, but do we have to have a physical magnet to produce a magnetic field? And the answer is no. We can actually make magnetic fields by using wires that are carrying current. And this poses a bit of a problem when designing currents, especially if these currents are very large in their magnitude, and if the wires are very close together, then they can affect each other with these magnetic forces. And we want to make sure that the circuit and all the wires don't inadvertently tear themselves out of their own connection ports. So when we get back, we will start chapter 29, and we'll see you then.